Take it away, Ryan.
Welcome to the December 16th, 2025 meetup of the Oklahoma City JUG Java Users Group. I think I was not a member yet 20 years ago, on December 16th, 2015. Oh no, wait, yes, that was in 2005, yeah. I certainly was not. But this group started back in like 2005, right? And the computer club. When is our 20th anniversary? Does anybody know?
We have
we're probably past it, I guess.
Probably. We need to get a hold of Brian Sheldon, see if he remembers.
Yeah, it's been a part of the user group tradition, nationwide thing Java groups do. Anyway, this time I have one slide, and you're looking at it in this talk. So this is going to be about Voronoi diagrams. Who's already tried to play around with those and look at those? You have what you use it for? I'll wait until after the piece.
Mapping out the regions of the country that are closest to each NFL team.
Oh, for fun?
Yeah.
Yeah, the regions of the country. So if each one of these dots was an NFL team, you could sketch out who's closest, which team is closest to you, right? By one of the regions. Yeah. I got interested in it just because I would do professional enterprise software for a living. I hate software upstairs here at Starspace, and you don't get to do a lot of algorithms in your enterprise software work. So I had a lot of fun for the last couple of weeks learning all about this, and so now you guys get the benefit of the learning. The learning is all in Java, so that's why I'm on these slides. Up until this meeting on the program, which I'm going to get out that you're looking at. So if I move my mouse around, the diagram changes. What do you think's happening? What's that doing?
If I had to guess, you're recomputing the whole thing, treating the cursor as one of the points of interest.
Yeah, the cursor is one of the sites, and every time you move it, the shape changes quite a lot, right? Why? What's that? What do you think that shape? What's defining that shape? Let me get it really close to those other 2 points, right? You kind of see there's that yellow dot in between them. It never touches any of them, right? But it's their territory, right? So you can use this algorithm for a lot of very practical things, right? And it is used already in wide area networking. It's used in business to find regions, like it did for the NFL teams. You could do like, what pizza restaurant should I order from at my house? But what's more interesting about it, I think, when it moves, right? So if, let's say you have a whole bunch of drones, or let's make it simpler. Let's say you have a whole bunch of Roombas because you have a super dirty house, and they're all moving around. Like, which one should go to the corner? Depends on where all the other ones are at that particular time. So having the algorithm available not just as like a static map, but in a dynamic way is pretty useful, which means you need it to work pretty efficiently. So I'm going to start with basically just how the algorithm works. And so this is going to be our site in question. And the very innocent, naive implementation of the Voronoi diagram is you just start with the entire screen is the region for that guy, right? And then you go one side at a time, and you do what's called a half-plane clip. So a half-plane is infinite all directions on one side of a line, right? So you take the two endpoints, the two sides, you find the midpoint, and this is the perpendicular bisector, so I got to do some geometry figuring all this out, right? And then that's the line, everything on this side of the line is closer to this side, and everything on this side of the line is closer to that side. So now I know that definitely across that line is not my region, right? And then do it again for another site. So here's another site, and it's got its half plane, and then what's left, you're doing a subtractive clip of the same region over and over again. So I'll do it again. That one was a little closer, so the first one was kind of wasted, right? If you're trying to do an efficient algorithm, it's too bad I had to compute this one and then just compute the next one, right? But you continue to do it site by site by site by site. And this is definitely a sure way to get a Voronoi region for a single site. I'm just going to get all the way to the end. Do you see how many of those are not really necessary, but we're still doing them? Right? Looks like I deleted it on the last one. So I can reset and do it again, right? And we'll have fun with that. So that's the half plane clip strategy for coming up with what a region is for a site. It only works in 2 dimensions. It would have to use planes instead of lines in 3 dimensions, and there's a whole other algorithm I didn't have time to code called the line triangulation. So maybe you guys can get me in the summer. It'll take me about 6 months to have this much time again. So but maybe May or June, maybe we'll do the line triangulation. So let's just do the whole board that way, right? So you can do that same process for every single site on the board, and you're going through all the other sites for each one of the sites. So what's the complexity of that algorithm? Anybody just off the top of your head?
Oh, log in.
N squared.
I don't know.
What was it that?
N squared.
What's n squared mean?
You loop through all the nodes twice.
You loop through all the nodes for each one of the nodes.
Yeah, for each one.
Yeah, exactly, right? And if I had 100 sites instead of 50 sites, it would be a square, a power factor of inefficiency, which we don't like that, right? And so for very large, and you can imagine on maps or something, like there's a lot of very large domains where you would use this, and that might not be the most efficient way to do it. So there was a pretty bright guy in the 1960s whose last name was Fortune, and I don't know his first name, which is why we call it the Fortune algorithm. And what he decided to do is let's not revisit every site over and over and over again. Let's start, I'm going to do just a subset of these. Let's start at one end and kind of work our way down and only visit each site one time. So you have a sweep line, it's called a sweep line. This is a Fortune's algorithm, he wrote in a paper, somebody later improved it. That's what we use today though, to do Voronoi algorithms. So you have a line, and what this line is like, this is all you know about the space. So as you go down, now the implementation is a lot more, you have a priority queue, we'll talk about how you implement it, but the theory of it is, you kind of progress down the space, and every time you encounter a site, now you know more about the space. So everything below here is unknown. Everything above the sweep line has been seen, and so far we've seen one site, and I drew a little parabola on there because this whole thing is quadratic. You need the parabola because what it tells you is, for sure, anything above the parabola is closer to this site than anything else on the board. And you don't know anything to the sides of it really until you get further down, because there could be other sites very soon under the sweep line, right? So as you move the sweep line down, more and more of the reach of the domain of the territory becomes certain that it belongs to that site, and that's what the parabola defines. So when you're working on the algorithm, you use these parabolas. Here, I have a little equal distance thing I put on there. You use these parabolas to indicate this is the distance. These are all the points that are the same distance to the sweep line and to the site, right? Basically, that's what the parabola means. It means everything that's equal distant to the sweep line and the site. Right? So you work your way down the diagram, and you get more sites eventually, and they have their own parabolas. And this is where I was coding in the next part, so this is not working right. So I'm going to go to my bigger line, and the lowest parabola for each x is the have it so it'll stop. The lowest parabola for each x is basically the area that belongs to that site as the beach line moves down. So that's called a beach line. It's like the front, I don't know how they call it beach, but it's like the front edge of all of the parabolas that we can see. If you do it the other way, you can just see all of their parabolas. Every one of them gets a parabola that opens as you go down, and it intersects with the other parabolas. So you want to take like any spot. How do I do this? I thought I had a pause. I guess we're just going to watch it do it like this. And the part I was trying to get a visualization for next is when you watch one of these things disappear, pop, like here goes, boom, that one just disappeared, then that one disappeared. Each time one of those disappears, I kind of have it where you can see it on this one, is the time when, I don't know if I can get it closer on that one. Let me go through that, and then this. I can't get it to go much further down, it deletes them. Let's do it this way. Yeah, I'm just going to have to use this one. But every time you see one of those disappear, it's called a circle event. So like right here is a point kind of like equal distance from all three of these sites. And it happens to be that right when the sweep line reaches low enough, that the two parabolas from these sites intersect. At that point, it's the same distance from all three sites. So there's a circle that connects all three sites, and the center of the circle becomes one of these vertices. Right? Each one of these vertices happens at a time that the sweep line goes far enough, and then the parabolas intersect, and then finally one of those little arcs on the beach line vanishes. Right? So Fortune's algorithm is one where what you do is you start with a single, like you work your way down the scene, right? And I have this one where I'll pause. And each time you reach one of these sites, you record a site event. And that site event has a Y value. And then you just fast forward to the next site event. And then the next site event will be when this one over here is reached. And you see another parabola jumps in. Each time you reach a site event, you add an arc to the beach line. And so you have like this list of arcs going left to right across the screen, or in random in an array, right? And each arc has a site that it belongs to, and it has an arc that comes before and an arc that comes after. So they have neighbors, right? And as you add more sites to the beach line, you're splitting arcs. So I can kind of show that one on here better. You can kind of watch it happen. You can kind of see these arcs when a new site gets added, boop, it'll split the parabola that's above it. See that? Every time a new one gets added, it kind of pokes a hole and then splits the one that's above there. So you're turning a long arc into two arcs when you split it, and you're sticking a third arc in the middle. So that's an insertion event. So every time you have a site show up on the sweep line, you've inserted a new arc into the beach line, right? And now, the times that the arcs disappear are called circle events, because that's when you lose them, right? That's whenever you see one of these arcs disappear, you're losing it. Like right here, it's about to disappear, pop, and then right at that point, you know you have a Voronoi vertex, right? So you use the circle events to tell when you're going to lose an arc, and you use the site events to know when you're going to gain an arc on this beach line. So the algorithm just loops over all the events, which is not that many events, even though it's a lot of pixels, right? It's only one event, one site event per site, and one circle event per arc, because each arc can only disappear one time, right? So the only complexity to that makes it a little trickier is when you do a site event, you're splitting an arc into two arcs. So now there's two that have to disappear, right? And they can turn into two vertices, right? So you use a priority queue. Who knows what a priority queue is? What's that?
Oh, I don't know if I could define it, you heard it before.
It's different than an array, right? So fancier than an array. What is we talked about this at work the other day, right? So
It's a heap.
that's one implementation. It's a heap. What's that?
It stores the minimum of a collection.
Yeah, when you put stuff in, right?
Yeah.
So it doesn't need to be sorted later, right? Every time I put something in to my priority queue, it gets put in an order at insertion time. And it's done in an efficient way because it's organized in a tree, so you don't have to go, if it was a long array, you'd have to have an order of in operation to go find where to put it in, right? If it was, let's say you have a sorted array of numbers, and you want to put number 6 in, you got to skip all the lower numbers and then put 6 in, right? So they don't make a priority queue out of an array, they make it out of a tree. And the tree has an ordering guarantee where everything to the right is bigger, everything to the left is smaller, except the higher ones are always guaranteed to be lower than the lower ones in the heap, right? So when you put something in, it goes, and it finds where it belongs, and that's a log n operation, because it's a binary tree. So it doesn't have to iterate 100 items if there's 100, it only has to go 10, because it has to go down that many layers in the tree, right? So Java has one. So in C, when I'm doing admin code, and I'm inviting all you guys to be on my admin code leaderboard, I have to make my heap in C, right? But in Java, there's just priority queue. You just use it. And you just stick stuff in it, and pull stuff out of it, you give it a comparator so you know what order things are going in. I guess I could show you guys some of that code here. So my Fortune context, this is on GitHub, and the font is small. Does IntelliJ let you make the font bigger? How about Zoom? Ooh, look at that. Yeah. So my Fortune context has it's a little bit long, right? But it has a priority queue of events. And as the sweep line moves down, you stick, I had to learn a little modern Java, because I didn't do Java for a living since, what was the version? Probably when 1.8 came out, which now that's a long time ago. But anyway, now there's this cool switch where you can you can match on a sealed interface, which I learned about at the Jug at one of the recent meetings. So I decided to implement my events that way. So now I've got this sealed interface event, which has site events and circle events, right? And all it does is give you back the Y address of that event. And a site event represents when a new site gets added to the beach line. And a circle event is a little more complicated. Circle event not only has a Y location, but it has a center of the circle. And what's going to be in the center? What does it cause on the graphics?
Vertex?
A vertex of the Voronoi diagram. I heard a voice, but I don't know who gets credit for that. That's right. So that goes to the center. And then the disappearing arc is the arc that actually has to get removed from the beach line. So once you've drawn that vertex, you do not want that arc around anymore to confuse the algorithm. So you have to remove it from the priority queue. So you simply stick all these events into the priority queue. Where my queue is. Here's my event queue, and I gave it a comparator that says you simply compare these events on Y, right? So I already know where all my sites are, right? Because when I run my app, I have a bunch of them get randomly generated, and I have X and Y locations for all these sites, right? So I can just run through all the sites and stick them in the priority queue as site events, and that's how the whole thing starts, right? So they're all in there, and what order are they in after I stick them all in there?
Y order?
Yeah, Y order, and in processing, which I should do an advertisement for processing. Processing was so much fun. But if you guys do any graphics programming in Java, that's what this was made out of. It's an open source library called processing. Some people, I met a guy who was at our Java users group, his name is Roy. He told me he learned about Java from processing instead of the other way around. He got into processing first and then found out about Java and learned how to program Java. So it's a lot of fun. You can make 3D graphics in processing. I did not, I just did 2D graphics. But it's got the whole thing about frame buffers inside it. It's got vector math inside it. I got to learn a little bit about geometry. Look, it's even, got this little glowing thing, so it's got an animation loop, right, built into processing. So you just hook into all that stuff. Anyway, so I already have all the Y's in there. At the beginning of the algorithm, I just insert all these sites in there, and that's not enough. Now they're all in the priority queue, but I haven't got a Voronoi vertexes or edges yet, right? Vertices or edges. So then you just pop the first one off, which is what's happening. That's what I was trying to visualize here, right? You pop the first one off, and you get an arc. Pop, there's an arc. And that's the whole beach line. The whole beach line is one thing. So the beach line is just a linked list of arcs. Every arc has a previous and a next. It's very basic, right? And then when you add that, that you're done with that side event, then so you can get rid of it. It's not in the queue anymore. So you go to the next one, and if there's another side event, then you have to connect it to this one. So when I get two side events, you can kind of see these touching, but you can imagine, like if this one was very high up here, the parabola would be super narrow, right? So the two parabolas would intersect, but like way up there, like not on the screen, right? So that's okay. The beach line doesn't care. The beach line's like wherever the parabolas intersect, it could be Y value of negative 400,000, which happened to me a lot. And when you work on your own Voronoi, that's the stuff you end up debugging all the time. These crazy geometry values way off the screen, but it's actually real. The two parabolas would intersect way off the screen. But then as the line moves down, it widens out, right? So the only other thing you have to do besides add arcs to beach lines is when you add the third one, you have to split whatever one it's on into two arcs. So you have to do this, and then you have to put those back into the priority queue. So as you're working your way down, you're popping stuff off, but you're also putting things into the queue. There's a special event you have to put in there called a circle event. Every time you split an arc, you put a circle event into the queue. And that event may never get used. So there's a validity, right? And here's why. Like as the line comes down, every trio of sites has a circle event, right? You can imagine on here, every one of if you pick any three sites on the whole screen, you can make a triangle out of them, right? And you can draw a circle around that triangle, and that would be a circle event, right? But not all those circle events actually make any difference to the Voronoi diagram, because, like here, like not all the sites border each other. right? So if I have a circle limit of this one, and this one, and this one, there's not a vertex here, because there's a bunch of other sites in the way, right? So what happens is whenever that will be a circle limit in the priority queue. That, like, every triad that gets intersected ends up on there. Now, some of the ones that are super far away never bother to get created, because the arc that it splits is over here, right? So as the beach line moves its way down, like, there's no need for when one of these splits it, pop. It doesn't interact with those parabolas over there at all. It only has to insert the circle events that have to do with neighbors, right? And not what, so that's one big optimization. That's one place where this wins over this mode, right? Because this, you do have to consider all the neighbors for every site, right? But in this mode, you don't. In this mode, when it splits the arc, it's only having to consider the sites involved in that arc. And that's a huge savings. That's why this is order of n log n instead of order of n. Because we never even end up dealing with all those other triangles, right? Now, I didn't get to draw my edges and stuff on this one, but that's what I got on Fortune's algorithm. There's a bunch of places to go from here. First place I would say to go is there's a couple of open source implementations of it. So it's a lot of fun to code yourself. It's intricate and full of bugs and makes you mad sometimes. So like, actually implementing it can be, it's only worth it like because you want to do it. And I did, I wanted to do it. But this implementation you're seeing here is not my Fortune context. The one that's moving so fast here is an open source one that I found. That, I don't know, some of you guys, the only one who did Voronoi might have already found this one. It's called JTS, and I don't even know what JTS stands for, but Location Tech JTS is an open source, via MIT licensed Voronoi implementation. You can just grab and hook up. So it's not just a priority queue, it's all of it. Side events and circle events and everything, and optimized to go fast, which is kind of useful, especially if you're dealing with a whole lot of data, right? That's what I used for my title slide. And then where I wanted to go after that was there's kind of two interesting places. If one of you wants to follow up and do a talk on one of these, or maybe I will, there's a couple of interesting directions. But one of the directions you go after Voronoi is you can do weighted Voronoi. So instead of each site having equal reach, you don't just use the distance. Some sites are have more power than others, right? So if you think of these as like Roombas, some have more battery than others, or they go faster than others or something, right? So you would then compute the distance between these differently. Like if this one was twice as strong as this one, then the line would be over here. Maybe it's like this one's LeBron and that one's who? Basketball fans.
Shay.
Right? So he gets to cover more territory in the zone defense than him because he's not that good at basketball. Right? That would be like a weighted Voronoi implementation. And a lot of times you'll do that. Like a pizza restaurant that has more delivery drivers might need to control a larger region than a pizza restaurant that has less. So you use weighted Voronoi for that, and it actually works with exactly the same algorithm. It's just the one step where you compute distance, you do it differently, that's all. The other one that's pretty interesting is Manhattan Voronoi. So instead of straight line distance, you use horizontal vertical. That's kind of useful for like city blocks and stuff like that. I want to know pizza restaurant regions, you wouldn't just do, right? You wouldn't just compute straight line distance. You'd have some other algorithm for what the distance is to a point. And it just looks really neat. I actually probably find one of those. Let me see if I can get one on here. Manhattan. It's funny how good Google is. I'm gonna do it live in the. Yeah, there's a Manhattan one. See how they look? It's all like blocky, right? Because it's using Manhattan distance to figure out the regions. Why is that looking different than my screen? So that's another neat place to go. And then one I really wanted to explore, which I didn't find a lot of literature on yet, is region splitting. So imagine your objective is to distribute the sites in a smart way. And you've got some that are already done. Maybe these are the people you sent out to do your political campaign door things, right? And I know I sent this person here and this person here and this. Where should I send the next person? And these guys are gone. They're already out on the street, right? So like, I can't tell them to go anywhere different. Well, I want to find the biggest region and split it, right? And put the person into the region that's the least served. And humans do this in their brains pretty easily. Like if you guys wanted to find where to send a new person on here, you probably have a good idea that you wouldn't want to send them here, right? Probably he's not going there. You do that just visually, right? Well, if we get a computer to do that, there's like an algorithm for that. So you do region splitting. So that's one next step I want to go for Voronoi. And then, of course, the next place after that is I want to figure out how to do it in 3D. But I found out that's a lot more research. It's not just like a little tweak of the algorithm. It's planes instead of lines. So it seriously changes it. But video game people do a lot of that too. Like in flight sims and stuff like that. So that's another place I will go next. And then there's an inverse. So instead of regions, I did a lot of reading about this because I was going to make a visualization after it. Same exact diagram, but instead of describing the regions, you have the points. So you can get the distance to the Voronoi vertices. They're called Delaunay triangulation. And what it does, Delaunay triangulation is super valuable because it uses pretty close to the same algorithm, but what you come up with at the end is triangles. Like you're able to split a plane up into triangles based on a bunch of points, and 3D graphics means a lot of that because everything in 3D graphics is triangles. So it's also based on the same underlying algorithm. So what I'm going to do with this, I mean, I've already got it up on my GitHub. You can go get it. I haven't got my latest commit up there because I was working on it right before this. But I'm going to do two things. I'm going to show you where you can get this and download it and mess around with it and fix all my bugs. There we go. So this is done in processing. I just stuck it out there. I didn't put a license file on it yet, but YouTube folks, I will know by the time you're done with it.
Too late.
Yeah, exactly. But you're free to. You have my verbal permission to go download the code and just don't sue me for it. That's the MIT license, right? This one says take it but don't sue me. But I don't know how you would sue. That's the code I showed you today, and it's kind of got a little nice little. The front end gives you an example of using processing for 2D animation, which is kind of fun too. You can find that on the net. And then the other place I wanted to invite you to, and there's an OKC Jug channel on Techlahoma, is I do Advent of Code, and because I was working on this, I'm not done yet. So you can still pass me if you get on my leaderboard. And this is all algorithmic stuff, kind of like what I just did, but I haven't found Voronoi here yet. But I found some other pretty meaty algorithms. So my private leaderboard is this one, and here's my code. So I'm going to go paste that in OKC Jug if some of you guys want to. Now I'm doing C this year instead of Java, so I'm at the wrong user group. But I will still like to. I would still like to see you guys on there, and then every year we can go check up on each other's progress. So where's UG Java? Why is it not here? Let's go add that. This is Techlahoma Slack. So how many people know what Techlahoma is? Are you sure, Jason?
I have an idea.
You have an idea? Oh, wait, I looked up and all the hands were down. How many people don't know what Techlahoma is? Oh, okay. This Slack I'm in right now is part of the Techlahoma Foundation. This is my admin code. We have an admin code channel for not just Java stuff. My admin code leaderboard. There we go. Techlahoma is a 10-year-old Oklahoma-based nonprofit. We used to have the Jug way before Techlahoma, but we would have to call Robert Half from GDH and get him to pay for pizza. So Jason, how'd you get the pizza paid for today?
Techlahoma paid for it.
Not yet.
Well, they will.
They will.
I hope.
Jason bought the pizza, so you can thank Jason, and he delivered the pizza, and he served the pizza, so we can all thank Jason for making this user group happen. But also, Techlahoma reimburses. So it's a nonprofit that's we've got to make it easier to have groups like this. In Oklahoma City. So Techlahoma's been a long-time sponsor of the group. Are we official for next year? Did you put that page in?
I need to.
I don't know. We have friends. Hopefully we can make sure this is an official Techlahoma group yet another year. One of the qualifications is 2 leaders, and one of the leaders does all the work. So Jason. And then the other qualification is that you fill out some forms. And I don't know. There's probably a bunch more rules and stuff, but we've been part of the Techlahoma thing for a long time. This is Star Space, so I got that on here. very profitable, but it's where I work. And it's a co-working space, so my office is upstairs, businesses can come here, people can come here, for different amounts per month, they work on techie stuff and non-techie stuff, we got some real estate people in here. So, those are two of the, do we have any more sponsors?
I think that's it.
That's it, and did JetBrains used to sponsor us, we should call them, I put their thing up this whole time. Right? What
Yeah.
happened to that? We used to be able to give out JetBrains licenses, remember that?
Yeah, it's been a
That was
while.
pretty nice of them.
It was. I need to contact.
Yeah, I'll take one of those.
But you can support the group by offering to do a talk like this in January. We would love to have another meeting and have one of these talks, something that you can do like I did and find something that you want to learn. So that's a lot of times why I do talks. I want to learn this, so I'm going to go make a talk about it, and then I'm going to sweat for 2 weeks while I'm getting ready for it, which is why we didn't have slides on it. But I learned a ton, and then everybody else gets to learn from each other. So you go learn something that you're interested in, and we all get to learn from you, and that's what the tech community is all about. So I look forward to seeing some of you either do something completely different. Jason's done two that I would have never thought of until I saw your talks, and I totally appreciated that. I didn't use JBank for this.
It's a shame.
I just used, but I did use Java 24 and some stuff I learned in your talk, and in the Kansas City and stuff.
Mm-hmm.
That's who came last month, right?
Yeah.
What was his
Billy Carando.
Billy
Carando.
Carando. We
Carando.
appreciate that as well.
Carando.
Yep.
I just butchered his name on video.
So, Paul didn't sponsor, but I did tell him he could ask something of this group. So you can go ahead and ask if you want about a little bit. So you teach Java, right?
Yeah, so I teach remotely at a small liberal arts college. It's a class in Java. It's for a competition called Battle Code, which is every January at MIT. It's basically like StarCraft, but you write the AIs for it. I don't know, a lot of you seem like my age, so you might know StarCraft, but you're programming an army of bots. There are two sides. There are different rules every year, so there's the specs for this year are going to be released on January 5th. Students form teams of up to 3, they compete for prizes, they like sit in a big auditorium and watch the algorithms play. It's like a ton of fun. And I signed up to teach a class. We have 9 students registered, and it would be, and then I got a job, which is unfortunate. Because I really I have a lot of fun with this. I taught it this winter. I had 3 students, and it was a blast. So if anyone is interested in teaching or coaching, hit me up. You know, the Tech Mormon Slack. And just talk.
Would this be volunteer paid? How does that work?
It's a complicated question. It's paid, but you have to live in certain states. I kind of like snuck my way in through like bureaucracy this time. Yeah. So they don't know I'm in Oklahoma, or they're not like paying too close attention to it. But yeah, that's the ask.
Yeah.
And
So if somebody wants to coach Battle Code, we have somebody to talk to. He's got a bunch of eager students ready for leadership and learning, and it will be a job.
it will be a job.
So you're at the right group for sure. Yeah. So anyway, I didn't ask the president, but I figured it would be appropriate. You know,
Your
Battle Code
presentation.
sounds like a ton of fun.
It does. All right, now I've got a bunch of questions.
All right.
Did you implement all the beach line, all that? Did you implement it yourself, or was that from a third-party library?
This screen is from JTS.
Yes, but the other
All
one
the other screens I did.
you did. Okay.
And I was working on it an hour. And I didn't finish everything I wanted.
Okay. Next kind of dumb question: as that beach line drops and the parabola widens, what are the parameters there? Why do those lines, the parabolas
Yeah,
widen?
so I was working on that. That's why I made this little cluster. That's what the third mode of this one's for. So as the line drops,
Okay, and that dot, remember that. I'll come back to that.
yeah, that is not in fortune. I just put that there to illustrate.
The little white dot there
Right,
is
that
okay.
fine. It's not fortune.
Just an illustration. Okay.
Yeah. The parabola just represents every point that is the same. That's what this is. Every point that is exactly the same distance from the site and the beach line. And as you can imagine, it could go on forever. There's no matter how far east or west you go, there is a point that's the same distance from from the line and from that. So the parabola is all of those points.
Okay.
And that
So
means everything on this side of the parabola is closer to the site, right?
Okay,
Everything up from the parabola is closer to the site than the line.
okay, that helps.
Yeah.
How do you detect parabola collision?
Well, then you just set them equal to each other, and I got a page full of algebra upstairs.
Okay.
But it's just, you
Well, that's
take the
good.
equation of a parabola, like, let me do this one again. Right, this is the mode where you can see them all, but they're kind of faint. Ooh, they're extremely faint. Here's like two crossing, right?
Mm-hmm.
So that point where they cross, they have, each parabola has a focus, which is the site, and a directrix, which is this. And it turns out there's an equation for a parabola given the focus and the directrix. So I have two different parabolas, focus directrix, and they both have the same directrix because they're both using the same sweep line. So it's really just the focuses that are different.
Okay.
So you set them equal to each other, you do a lot of painful algebra that I was rusty at, and cross out terms, and then you end up with a simpler expression that says, give me the x, because you're just looking for an x,
Mm-hmm.
where the two are equal. And that's the goal of all that algebra. So that probably took me 10 hours longer than I wanted it to, because I have not done algebra in many years.
Yeah.
I'm a little less rusty now. But yeah, that's it. It's just you set the two parabolas equal to each other.
Okay. And then on a more practical level, once you have your regions defined, if I can summarize all, so looking at that, so if you are in a given region, you know that the point, the yellow dot, the green dot, whatever, is going to be the closest location to you at that point.
Yeah.
Until you cross the region line, then you know rather than going to the green dot, you're going to go to the red dot now.
Yeah.
So from like a logistics planning, map, travel, whatever, it kind of sits in that space in terms of practical application.
That one direction is you starting with a point anywhere, and you went, oh, I'm in this one, so I go here. That's one way to use it. The other way is, I'm in a pizza restaurant, should I take this phone call? Right? Or you said, so you could be coming from here and trying to determine how big a trash bag should I carry to go around the park and pick up? How big is my region is another question you might ask, right? Or if I'm a Roomba, how much battery will I have when I finish? So you might want to ask about the region, or you might want to ask about the point.
So when you call the Pizza Hut main number and you give them your address, they can use something like this to determine the closest
They most
location.
definitely
Okay.
are,
Yeah.
yeah.
Okay.
But it's neat because you don't have to call an API, you can just do it yourself with this, right?
Yeah.
Which is a lot of times, my real job is mostly APIs, everybody, so like I'm used to gluing APIs together, but it's nice to be, oh yeah, I don't have to call somebody, I just do it, right? Yeah. You can also use it for optimization, so you can take this whole thing and find like the shortest lines, and then move sites to make them longer. Like, so you can do operations on the whole diagram after you've computed it, you can find inefficiencies. So like if I'm a data center and I've got a bunch of routers and they're all connected by cables, and it's like there's 14 hops to get from here to here, but everything else is 3 hops, this will tell you that, and you can like, oh, put a link, So it gives you a way to optimize networks of things, or polling people, right? I'm gonna go put a person over here because there's not enough, we're not gonna reach enough voters, or you can imagine translating that to a lot of companies.
Yeah. I always like to take a practical use with something like this.
For you guys, like you have to figure out how many mirrors you're gonna have for downloading your product, right?
I don't.
Somebody does, right? So
Yeah.
you would know to add a new mirror if there was like too many downloads from one of these or something like that. Where should I put that mirror?
Yeah.
Or Cloudflare does that for websites, right?
Hmm.
Yeah. Paul?
Interesting.
These are static sites, but does it work for dynamic sites? Like this is a kind of a fabricated problem, but I was volunteering planting trees, and every team had like a list of tree sites to go plant, but sometimes someone would miss one, or the teams would just give up and go home.
Sometimes people would what?
Give up and go home. And so the other teams
Had to fill in.
were moving around, and it was kind of ad hoc. They would figure out who was closest and tell them to come plant this tree, but could Voronoi be dynamic? Like could the
Yeah, that's why I made the animation where I can move this around and show that. But
so you could have like 10 mouse cursors up there moving.
they could all be moving all the time.
Okay.
And then some of the cool animations I saw online, it's like planes in air traffic control, and they're all moving, which looks cool, but it's super confusing.
Playing a computer, yeah.
But I mean, to do that, you would need a central point where the locations of all of the tree planters was in one computer at the same time.
That's true.
Or else you wouldn't be able, you have to have all the information in one spot.
But they could GPS location back to server that would map all that and then can,
Oh, yeah, you can.
Direct
That's
or-
cool, because you can see them like giving up and leaving too, like, where'd that team go? Yeah.
Ryan's quit on us again.
Yeah.
Second question. So there's a heap. So in Fortune's algorithm, when you're going down, there's a heap to keep track of the lowest parabola. Is that right? Or
All the events, so there's, both types of events go into one heap.
okay, and
So
then
site events and circle events are all put into a single heap.
and what's the quantity that's being minimized?
This is the Y location, which represents, theoretically, that represents this sweep line. So as you heat stuff off the heap, nothing can go back in time. So it's like, as the line goes down, you can imagine time going forward,
Yeah.
and you never put anything in there that's behind you. So only things in the future are being put into the heap. And then you just want the next thing that's gonna happen. So that's Y represents, because it's a line passing down, it represents the next event that's going to occur. So if you put an event in that's really far down the page, it won't come up for a while. But if you put an event in that's right in front of you, it's gonna come right back out, and the next time you pop.
So if you have to, you're saying like delete and mark. Are you deleting it within the heap?
When you process a circle event, when I pop a circle event off the heap,
Yeah.
then I'm going to do a bunch of maintenance. I have to so there's two steps. When I put a site event on the heap, I split mark, and I put both of them back on there, and the new one, right? And then when I process a circle event, I have to destroy, and create a vertex. So that's the maintenance, and that's why you need the heap. So you're putting events on there that say, we just had a circle event. Oh, it was behind me on the line, so I can ignore it. Or, oh, this circle event has been marked as invalid. Because when I process a circle event, I could invalidate other circle events, right? And they're all the ones connected. Because if an arc disappears,
Yeah.
then any circle events having to do with that arc are no longer needed. So, when they come up again, you're just like, oh, forget that one, and you skip it.
That's what I was wondering, is whether you search through the heap, which is not efficient to do, or whether you mark it as invalid, and then when it comes up, you ignore it.
Yeah, you only ever have to ignore it if it comes out of the heap. Because if you make it to the end, you just forget about everything that's still in the heap because you're done. Right? So you don't have to process the whole heap to the bottom. You just process until you get the whole thing done, and then you're like, I'm done. Because I got to Y equals the bottom. Which is, I kept trying to figure out, why do I still have a beach line? And I thought I had a bug. But I don't have a bug, because there's no more sites.
Yeah.
So I don't need the beach line anymore, throw it away. Right? So that was where some of my time got wasted. I was like, how do I make it go off the bottom? I don't know if you can see it from way back there. There's a little beach line poking up above the bottom.
Yeah, I thought it was because it reminded him of like waves on a beach or something like that.
It looks kind of like that, yeah. Let me see, reset. Sort of like waves on a beach. Yeah, I don't know. I don't know why. That's called the beach line in his paper though. So it's Mr. Fortune. I wish I remember the name of the guy who optimized the algorithm. They even found a mistake in his original paper too. And when I was researching for this, I did know the guy's name, and so I'll have to look it up. Because implementation took a long time.
Yeah.
So the importance of storing all these events in a heap is you want to be able to know what's the lowest on the page as you sweep down.
The other way around, the highest.
Highest.
Well, I have Y going from 0 to high here.
Yeah.
So if you flip it over, it would be you just go up. The direction you draw it doesn't matter. Just up.
Okay.
But higher value of Y is later in time.
Okay.
Yeah. Yeah, so, and I don't know how you would do that in 3D. Yeah, no. What's your name?
Luke.
Luke, sorry.
Yeah. I think that you mentioned a certain like use case where you would path between like two different sites, right? Or like, so after you computed it, that's like one possible use case, right? Or was I confused there?
I read about them using it for
Yeah.
optimizing networks. I did not read about how they did that.
Okay. I'm just wondering, and I might be confused about this because it's been a long time since like my algorithms class in college. Why would you use this kind of algorithm over Dijkstra's algorithm for like a shortest path like search, right?
Well, Dijkstra will let you find, so there's an algorithm called Dijkstra's algorithm, which is for finding a path through a bunch of nodes that have distances. So you might have like, so if you were on one of these yellow dots, how do I get to another one with the least number of steps? Would be like, Dijkstra does that. Yeah.
My understanding is that Dijkstra, you know, you have your graph, your tree, and the nodes already have like specific discrete weights, but you know which ones, like each node is like only connected, but here this is more like physical space where you don't know like, you don't know like which like where the boundaries are going to be before you compute this. That's my thinking.
Yeah, I know I use something like Dijkstra called Crustal, I think, to know how to cut paths to make it in a graph. This seems like it would be useful for adding. Because, hey, look, this is a really big distance here, so I should connect these two. And then so that's region splitting, right? And so I don't know if that's what it is, but it seems like I couldn't do that with Crustal or Dijkstra because like I already have to have a path that's available.
Yeah.
Right? And here we're trying to add a path that's not available, I think.
So it seemed like the difference would be here, maybe saying the same thing you just did, but if you're inside a region, it's be able to find the closest vertex in that region, whereas Dijkstra would be the fastest or the shortest distance between two, for like, points on the shortest path along the edges, whereas this is not concerned with the actual edges of the.
I am no more confident than he is. I mean, that's all speculation.
Yeah.
I didn't read a description of solving that problem with Voronoi. I just read a claim that it was done. So I'm also speculating as to why it would be done that way. Yeah. But I mean, that's what kind of got me interested in it.
Yeah.
I think you also mentioned that there were a lot of bugs happening because of parabola intersections that happened off the screen.
For me, yeah.
Yeah. So do other implementations of this take into consideration, like, the problem space of concern and say don't calculate any like parabolas that are like in this case off the screen?
Well, yes and no. One reason it's yes is they have the degenerate cases where points are really close together or exactly at the same Y. They're all really well documented because a bunch of other people ran into them, so clearly they do factor those in. Those are not the ones I had trouble with. My unique challenge was nobody apparently ever visualizes it. So me trying to make a visualization, I have to consider all the positions of the sweep line in between events, which are not necessary in regular Fortune. You just skip straight from event to event in Fortune. I decided to be ambitious and draw all the points in the middle and got myself a whole bunch more degenerate cases that most people don't run into is what happened to me. So, yeah. And here I was trying to get it so I could show you guys where it would disappear one, and I'm not selecting the right arc, and so this is my latest bug I'm working on. Yeah, visualization is more difficult than just execution.
Yeah.
Which I didn't expect that coming in. I thought it would be the same, but we don't do things because they were easy, we do it because we thought they were easy.
That is exactly right.
One other question, and I imagine this is covered in the paper, but are there any special considerations you have to make for floating point arithmetic with all the like algebra going on here?
The geometry guys, besides just Fortune, also this really interesting guy who wrote the algorithm for distance that I used in C, they're very strongly in favor of floats over hits. Like they don't mess around. floats are way better, because it's way, the floating point math is, well, I guess I cannot be as strongly in favor of floats as the guys who are writing the papers. But yeah, they make a point to say, you should definitely use floats instead of hints for something like this, and you're gonna have all these bugs if you use hints, so they try to warn me the other way around, I can at least confirm that much. No, floating point rounding is for some of the degenerate cases, because if you pass a point the wrong, and it's within rounding, when the event happens, because two are really close together, it can look like something was in the past, so they have these little epsilons that you use for comparison. I have a bunch of those in my implementation. I titled them capital X epsilon all the time, so that I would have a good, is it in here somewhere? Where's my epsilon? But, I actually experimented with that a little bit. I'm using 1/1000th, how do you do that here? Right now, as my epsilon, but it's not because I can't have any reason it's better than 1/10 or 1/100th. But you need to do something to, when you do comparing the two floats, to consider something equal, even if it's a little off. Especially because the way you want to see masochism, the way I decided to implement this was I separated the visualization stuff, which all uses floats because of processing, from the algorithm itself, and I had that in by itself in pure geometry, and everything there is using doubles. And so every time I would switch from the algorithm back to the visualization, I had to switch from floats to doubles and back, which just made it a little more painful. But I mean, doubles is the right thing to use for the actual algorithm anyway. Yeah. I haven't been Java in a while. Yeah.
Question upon like the native cluster. It's a bit not advanced, but like if I have a dependency that's on Java 8 and I'm running that repo on 11, will that collide? Will that be a reason why I'm not able to install that even cluster?
I have had problems the other way around. I've been on Java low version trying to use dependencies that are on a higher version and had problems
So
unsupported.
they should be equal whichever way.
No, they don't have to be. I use Java 17 dependencies in here, and I'm running on Java 24, and it's fine.
So your question is, you're running on Java 11, but using a library that was compiled with Java 8?
Yeah, something like that.
Yeah, that should be fine.
That should be fine.
Yep. You can't go the other way, because it'll give you some sort of a byte code or
So
version
8
mismatch.
cannot run 11, but 11 can run 8.
Yep.
Oh, okay.
Yep.
So high versions can run the lower versions, but
Yes.
the low version,
Yeah. And that is, just as a side note, when people say Java should do X because Kotlin does it or Scala does or Python or whatever, the Java architect group is very, very careful not to break that backwards compatibility. So they have to think through, if we add this, is it going to break anything in earlier versions? Because there are billions of lines of code running, so they're very, very careful not to break things. So generally speaking, you should be able to take something that's compiled 10 years ago and run it on a modern JVM. You know.
And even this was, processing was pretty old. It's over 10 years old, and so I have some kind of older version of Java was written on. I think this one has some kind of JNI stuff in it.
Sweet.
And it figured that out. I'm on a Mac, and it downloaded the right thing from Maven, and I didn't have to do anything. I was very impressed with that. So I don't know if that's everybody's experience always, but at least this time.
It gets tricky with native stuff for sure.
So my dependency, I didn't end up fighting with dependencies as much this time as I have in the past. Yeah.
What are the implications for the little draggy, opener you had? You're just dragging around the point. We have a fully filled in Voronoi diagram, but then a point moves. How do you only have to recalculate the neighbors? Are you recalculating the whole screen each time? What efficiencies can you save if only one point moves?
I don't know of any savings. Now, if it was my fortune implementation, I would be able to assertively say there are no savings. However, this is the JTS one, so maybe they came up with some optimizations I don't know about. But because it's O(n) log n, it's very fast. So I think I'm 60 frames per second, and I've got compute to spare. I'm only doing 50 sites. Hey, you wanna play with it? You wanna put a big number? That'll be fun. I don't know, I mean, I'm gonna experiment and see. Let's see. So let's try, oh, that was 42 sites. So let's do 256. And
Sweet.
see what happens. So about a 5x improvement, or my randomizer's not very good.
Actually, it's really good because you shouldn't see a consistent pattern necessarily. It just
That's weird about my randomizer though.
it does
I think
ignore
that
some
part,
spaces.
Part of it is I generate a cluster in the middle so that when I zoom, it's a nice one, so I cheat. So for these are not as random as the others, but I did not expect the rest of them to be distributed. So this is my implementation with no optimizations at all. The beach line's doing alright. I mean, seems pretty good. Let's see how GTS does with this. I mean, right? It's doing the whole thing.
It was a whole lot faster than yours.
Yeah. Well, mine wasn't computing, it was just
Oh.
wrong. So, wanna go bigger?
1024. Let's
Another power 4, I mean 2 powers of 2 or something. Same difference.
oh. Yeah.
That's a pretty consistent issue, isn't it?
Yeah, my
It
randomization
is.
is horrible.
That is.
It seems really fast.
It does.
Alright, so it might be doing what he's saying, in which case we could keep scaling, right? Yeah.
The thing that interests me though is like, most of the screen doesn't change, so couldn't you, like, maybe you could just do some sort of variation on the brute force algorithm, but you only calculate you take the neighboring points to the point.
Like dynamic programming?
Something like that, yeah.
No, or if you keep the fortune, see, the fortune is a single pass now. So once you process the queue, there's nothing left in it. So you have to have another data structure. You'd have to change the algorithm. There's probably a way to make the algorithm do that, but the way, because it does a sweep line, it's a destructive on its own data structure as it goes. So I don't know how it's going to keep cache. It seems like there seems like there's an opportunity there though. There may be a paper in it. Challenge accepted.
Not for me.
Yeah. So it's chopping at 4,096. So this would be an illustration of the opportunity I think you identified, right? Look at this, it's chop, 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 chop. What am I getting, like 3 or 4 frames a second now? With 4,096? That's depressing. I don't know. Yeah, so that does seem like you have to make a different fundamental implementation. Wouldn't have to, that'd be something non-destructive. Very interesting. Alright, well let me take that number back down. But my computer didn't catch fire though. You know? Let's do like 12. Let's do a small number. It'll look much more natural.
Unless we just can't unsee it.
Yeah, exactly. Definitely my randomization needs a pull request if anybody wants to send it.
Do you remember that game Tempest
Tempest.
from the Atari 2600?
No.
It was like a spider web, and these things are coming out from the center, and you had to turn the paddle and move your ship around the outside and shoot it before it got to the edge. Anyone?
Yeah, Tempest.
I remember it.
Yeah?
That's what that looks like.
I think it looks like a really incompetent spider.
Well, probably, but still. Any other questions?
If you are doing this with the Manhattan norm implementation, like say for city blocks, would it convey the same information whether you have square regions or these, polygons of, in edges?
It doesn't make square regions. Some of them still have diagonal lines, but they're like the region boundary will have a diagonal line, so but the paths to the spot don't.
Okay.
But I think it's the formula you use to determine equidistance is all that changes. That's the cool part, is you just only have to change the formula they use to tell if things are the same distance from each other.
So then the graph would be functionally look the same.
It looked different. I mean, let's go back and pull it up. The Manhattan distance one. I think all I have to do is search for that. Yeah, that's a Manhattan one right there. Okay. I would like to see the output, not the source code this time.
The Manhattan version is like this in 3D, right?
No, it just means
No.
that the distance from one point to another is not measured straight line, it's measured in, you have to only travel east or north or south or west, and you can't travel any direction you want.
Oh, okay, yeah.
Mm.
And so it does end up with those diagonal lines, and I don't know why, but they have these like, it kind of still, they're all 45-degree angles, or it's like you only get 8 directions on the boundary lines instead of continuous directions.
Okay.
Yeah. And I haven't coded that one yet.
So those diagonal lines are a product of like northeast or southeast?
I guess, but I think you can only travel east or, so like,
So why wouldn't it come up with just?
It's the way the distance is measured is along cardinal directions. It's not like the boundary line has to be the same.
so all of these points are the same distance from these two if you are only traveling in cardinal directions.
If you're measuring.
That makes sense.
Yeah. But I mean, there's a lot more funky algorithms that people have plugged into this for the distance besides, like, these are simple ones that you find online, and then all the applications, like, are much more, you can put sophisticated stuff in there, amount of fuel in your pizza truck. You know, that's the way, so weighted Manhattan would have another look. And the part, I haven't even started researching it, I just started looking into 3D, and first thing I saw was, this is not the same algorithm, and it was basically like, you ever turn down a road and you see the big construction sign, it's like, don't go that way, so I didn't go that way. I will later, but 3D is a whole different animal, and interesting, yeah, let me see, types of Voronoi. Oh, variations, this is at Whitman College. They have pictures, please tell me they have pictures.
Fancy.
They have formulas. Relevant subsets. That's the half plane one I did, and there's the circle. That's a circle event. See how 3 points are all in a circle? That's what I wanted mine to show. Where the Voronoi vertex is right here, right? And that's the center of a circle that contains 3 points. It's beautiful. I wanted to make one. I will eventually get that visited. I wonder if it said variations on the title of the paper, right? Voronoi graph. There's the line triangulation, so you draw the line directly between the sites. And we don't care about that. I don't even see Manhattan in here. Are they going to give me a better, or what's this one? Multiplicatively weighted. Ooh. So, that's interesting. So the distances have a nonlinear element to them. Wow. There's a whole bunch of, so this one's region is like concave and these are convex. And there's a whole bunch of family of these. It's much more mathematical. Is there any more pictures? That's expansion and deletion. Well, I didn't find it in that paper, but yeah. Any more questions before I better wrap up? Comments, observations, recommendations? Compliments?
None of those either. All right.
Condescension.
Thanks, Ryan.